Okay, so we're now going to look at Module 6, Electricity and Magnetism. Specifically, we're going to look at Unit 5 and 6, which is actually a really nice section. Some of this is going to be revision from stuff you did in grade 10, and we're just going to put it all together because it lays a good foundation for grade 12. And it's really, this is no calculation, this is just theory. So, remember, and you've learnt this definition, that a magnetic field is a region in space where a ferromagnetic material will experience a force. So a ferromagnetic material needs to contain something, has to contain iron, nickel, or cobalt. Okay, one or more of those metals as an alloy is also fine. Now remember, let's just get rid of what I put there so that you can see the picture. To know if there's a magnetic field, we use compasses. These are called pointing compasses. They're tiny. They're about the size of a 5-cent coin, and they're very tiny, and they're actually very fragile. So they break quite easily because when they get dropped, they lose their magnetism. And what these magnets show me is that the magnetic field is going around in that corner. That way, it always goes from north to south because the north pole of the magnet of the compass points towards the south pole of the compass, of the magnet, sorry. Now, if we take a straight conductor, and this little green thing is simply there to hold the conductor in place. We have a straight conductor over here, and we allow a current to pass through it. The iron filings that are around it will create a specific field, okay? And that field is circular. It's concentric circles, they get bigger and bigger, but they are circular, goes round. This obviously means that there's a problem finding a north and a south pole because it's circular. Okay, so in order to get it, we use the right-hand rule. Now what the right-hand rule means, and remember, it's the right hand, it says that if you take your thumb, all right, and you point it, so you hold the conductor and you point your thumb in the direction of the current. The way your fingers curl around the wire will tell you the direction of the magnetic field. There is no north and south pole, but because a magnetic field is a vector, it needs to have a direction. So we have a sign convention because we can't all draw three-dimensional diagrams when we do this. So we use a sign convention. What you have to imagine is that this is a wire that's coming through the page or through the screen, all right? And we've cut a cross section of it. That dot means, all right, that the current is coming out the page. In other words, the current is coming towards you. So if you take your hand and you point your thumb towards you and you curl your fingers, you can see that your fingers go in an anti-clockwise direction. If it's going away from you, we use a cross. Cross means that it's going into the page. So if you point your thumb into the screen and you curl your fingers around, it goes clockwise. But you have to remember, it must be your right hand. If you don't use your right hand, it won't work. Okay? So, if now we have a single coil, and of course a coil means that we have parts that come out, parts that go in. We don't just get a simple singular coil. Okay? What happens is that here we go, we have parts here, parts there, so some of the current is going out, some of the current is going back in. How do we know? Because we can see from the power supply. So, using the right-hand rule, you can see the shapes, and what you need to notice here is in the middle that they reinforce, so there's lights in the middle because they're going in the same direction, okay? If now we make a solenoid, now a solenoid means that we take coils like this and we put lots of them. Okay, so there's lots of loops. When there's lots of loops like this, these magnetic fields interact with each other and they just get bigger and bigger. What that means for us is we end up getting a magnetic field that looks like a bar magnet. So if you look and I pretend that over here I have a bar magnet, you can see it's exactly the same direction that you learned last year. Okay, so it reinvents itself, okay? It reinforces itself, and you get this wonderful magnetic field that looks like something we know. Because of that, it means that we can actually consider the solenoid as having a north and a south pole. We have created an electromagnet, okay? So it's similar to a bar magnet. The magnetic field can be increased by, number one, increasing the number of turns. So let's just get rid of what I have there. But what I mean by number of turns, grade 11s, is increasing these things. Okay, so we wind it more. We can also make it bigger by increasing the current. If there's more electrons that are moving, because we're making this magnetic field by moving the electrons, then obviously we'll have a bigger magnetic field. Also, all right, but how do we find the direction of this solenoid, the magnetic field? Okay, it's also by a right-hand rule. So make sure you don't get the difference between here. The one we've just done says to us that the right-hand rule means that our thumb points in the direction of the current, and our fingers show the direction of the magnetic field. Now, what we're going to do is we're going to hold the solenoid with our fingers, okay, and the curl of our fingers show the can you see they curl around here and they show the direction of the current, and then our thumb points to the North Pole. So if I know the direction of the current going through the solenoid, then I know where the North Pole is. And if I know where the North Pole is, then I know that the magnetic field will go out and come back over here. Okay, so that's the whole point. The point is to find the North Pole. All right, so that leads us to unit 7. So what scientists realize is that a moving current, a moving charge, created a magnetic field. They then went, well, what if we have a moving magnetic field? Can that create a current? That gets us to induction. Now, if you look at the animation, you can see you have a magnet that's been pushed in and out of a solenoid, out of a coil. And if you look over there, you can see that as it moves, all right, the voltage on the voltmeter changes. So as it's moving, okay, we have a current being formed. That current creates a potential difference. That's a voltage. So when a magnetic field, so it's what we're doing with a magnet, and conductor move relative to each other, and we could move the magnet or the coil, all right, an EMF is induced. Induced means we make a magnetic field. We make it do a magnetic field, okay, across the ends of the conductor. So this produces a current. So if we have a magnetic field, this produces a current. Now, how do we make this current bigger? All right, number one, we move the magnet more. So we move it in and out faster. We may move the coil faster. We do something like that, okay? So we increase the speed. Number two, we use a stronger magnet. Now, please note here, grade 11s, we use a stronger magnet, not a bigger magnet, okay? Bigger magnets, just because they're bigger physically, does not mean that they are stronger. You can get very, very small magnets that are extremely strong, so just be careful. And number three, just like the last time, use more windings. Put more wire here. If there's more wire, there's more electrons available. If the wires are moving, okay, then if the charge is moving and we have lots of wire that the charge is moving, that the magnetic field is moving through, then of course, well, we'll get a bigger current. So the direction of the induced current is reversed when the North Pole is replaced with the South Pole. So here you can see, then when I push the North Pole in, I get the voltage going to the right, and then when I pull it out, it goes to the left. If I change this around and I put the South Pole in, it would go to the left first, okay? The direction of the induced current is reversed when the magnet is pulled out instead of being pushed in. This is very important. It's how we get alternating current, which is our electricity supply, okay, because the current is forever changing direction. Now, the magnetic field of the induced current opposes the motion of the magnet. So what does that mean? This is quite important, okay? So if I push a south pole into my coil, the coil creates a south pole because it doesn't want to have that south pole there, okay? It's trying to reject the south pole. It's trying to repel it, okay? So if I know where the south pole is, then I can find the current by using the right-hand rule. So in other words, I point my finger to my thumb, my north pole will be over here. So if I have my thumb pointing to my north pole over here, then the current goes this way around. But when I pull the magnet out now, all right, now the coil needs to attract the south pole, so it creates a north pole. So it does the opposite of what you're doing. So if I was pushing in a north pole, it would create a north pole there. If I'm pulling out the north pole, then it creates a south pole, okay? So it's really quite important that we get that. Now, the magnitude of the induced EMF of the conductor is directly proportional to the rate of change of magnetic flux linkage. In other words, it's proportional to how big the magnetic field is that the wire's in, and how quickly it happens. Okay, that's really, really, really important. So the magnitude of the induced EMF and the induced current depends on, number one, the area covered by the magnetic field. And by that I mean, how big is the coil? If it's a big coil or a little coil, that makes a difference. A big coil has a big area, greater magnetic field flux linkage, okay? The strength of the magnetic field, how big is the magnet, how strong is the magnet, okay? The rate of change, in other words, how fast am I moving the magnet? Now, that means either is the magnet moving quickly or is the coil moving quickly? You don't always have to move the magnet, you can move the coil, all right? So just be aware of that. And the number of turns in the solenoid. So in other words, how many loops there are. If there's 1, 3, 200, it makes a difference. How can we calculate this induced EMF? Well, this is the equation. That's an epsilon. It means induced EMF. N is the number of windings. 1, 3, 500. Delta phi, now this is new, is change in magnetic flux. Okay? And then delta T is time that is elapsed. The negative, this negative, has to do with what we were just talking about. It's got to do with how the north pole is created in the solenoid. All right, so that's the first thing. So we're not going to worry about it. What it does mean is that we can get a negative induced current. And that's okay. That's just a direction. That really isn't a big thing. It means nothing in terms of size. It's simply the direction. The nice thing is you just need to know this equation, okay? And essentially it's from Faraday's law, which is what the statement is we just did, but you just need to know the equation. You're not going to be asked to do any calculations with it.